So let's look at an example of blowing a fluid, maybe this is air, over a ball or a cylinder. It's a 2D, so it's a round object. And so right now we're given a uniform velocity comes in maybe, and then the velocity along the streamline right along the center that comes to rest touching the ball here on the leading edge is given by this equation here, which says the velocity vector is equal to u of x times I. In other words, it's purely horizontal. There's no y component, so it's 0j, no z component, 0k. And then furthermore, u of x is given by that. And so this part here without the I on it, that's u of x. We're asked to find the acceleration. So the solution. Acceleration, we'll just take our definition here, is given by the substantial derivative of the velocity with respect to time. And remember, we can expand that out. That is the partial derivative of the velocity vector with respect to time plus u times the derivative of velocity vector with respect to x, v derivative of velocity vector with respect to y, and w times the derivative of the velocity vector with respect to z. But as we said a minute ago, there are no v and w components, and so v is equal to 0 and w is equal to 0, and so we only have to deal with the first half of this. And so let's get the equation so we can see it there. All right. So we start subbing in. I'm going to give myself a little room. I'll start over here. So the first thing we're going to work on is this dv dt term, the partial derivative of velocity vector with respect to time. So we're going to get a d by dt in. And what are we taking the derivative of? The velocity vector. That's the whole thing. So v0 times 1 minus r cubed over x cubed, and the I hat goes right along with it. And then we have this term here to deal with, which is the u multiplied by the derivative of the entire vector with respect to x. So first we grab the u. U is this business here, v0 times 1 minus r cubed over x cubed. We're not grabbing the unit vector I, because we're just looking at the u component. And now we need a d by dx of the velocity vector. That's the whole thing again. So v0, 1 minus r cubed over x cubed. And this time the unit vector comes along because it's the entire thing. And so just for your reference here, this is the entire velocity. This is u, and then this is the entire velocity again. Okay, so if you run out the calculus on that, nothing in here depends on time, and so that's just a 0. There are no t's. If you saw a t, we'd have something, right? Just straight calculus. This here is just a multiplier, so we're going to bring that along. v0 times 1 minus r cubed over x cubed. And then when we take the derivative of this with respect to x, we're going to get a v0, we're going to get a minus r cubed, right? Because the derivative of this 1 is going to be 0, but this term has an x cubed. And then the derivative of 1 over x cubed is going to be minus 3x to the minus 4, following the power rule. And that I comes along just like any other constant multiplied against this would. So we can do just a little bit of arithmetic or algebra here to simplify this, and it becomes minus 3 times v0 squared over r times 1 plus r per x cubed all over, what is that, x over r to the 4th. And so that's our answer. Bearing in mind that that algebra was a little bit inconvenient to do and wouldn't expect you necessarily to simplify things like that if you were, say, in a limited time experience like on an exam. The thing that's neat here is that this is the acceleration along the streamline. And so if you plug in a value of x, in other words, if you pick a location that you care about, say this one right here, that has a value of x. We could plug that value of x in here, everywhere you see x's, which would be there and, well, here. And it would spit out an acceleration vector, which means we are really close to putting something like m on there and being able to apply laws like F equals ma to actually predict the motion. Right now we're just describing what is the acceleration, but it's not a very far leap to get from there to what is the force that caused it.